Okay, this is a really important lecture because it's starting to get at the calculations involved, some of the foundations for the probability calculus. Remember, this class, even though it counts for the math requirement, focuses on ideas and concepts, not the math and the computations as such. So we're going to set the prepare the ground carefully by looking at those concepts and then sort of while emphasizing the concepts, getting into some of the technical notation. There's no avoidance of the technical notations. So the first thing we need is some talk of logical connectives. This is building upon our initial lectures on deductive logic. So and in English is represented as this symbol, what's called the ampersand. Or in English is represented as this V. Sometimes you think of it as a fork in the road. That's why it's sort of like that. You can go on a left path or a right path. You have options. And then not is what's called the tilde, this squiggly line. Okay? So equivalent to that is set notation. You're going to see this sometimes in the book and elsewhere, but we're not going to emphasize it so much. This U thing is short for union, which is like or. This upside down U means intersection, the meeting of two things, which is and. The intersection of two things is saying this and that, where they meet together, which is also what it's called, the meet. The union is sometimes called the join. And then not is equivalent to what's called the complement. So A prime, the complement of A, the opposite of A. Don't worry too much about that. Okay, here's the first thing. The notation for probability is PR parentheses. You're saying the probability of an event. What goes in the parentheses is an event. Another convention is that when you calculate that number, probability of an earthquake on the Big Island, for example, they always lie between 0 and 1. You can't say 100, you can't say -10. All probabilities are percentages between 0 and 1. 0 is 0, and 1 it would be 100%. When you think of percentages, like 80%, you translate that back into decimals, it's 0.8. So that's why all probabilities lie between 0 and 1. A sure event, one that's guaranteed, has this funny symbol called omega. So a probability of a guaranteed event is 1. There are such things. We might talk about it later. Mutually exclusive. This is the first thing that's important. Things are mutually exclusive, ME, or disjoint. I use both terms. The book uses both terms interchangeably. When, if one occurs, the other cannot occur. You can think mutually exclusive. That's like a tray that you get at lunch where it's got the separating compartments. Mutually exclusive means if you have rice in one compartment, you cannot have corn in the same compartment. They're separated. So disjoint or separated means if one occurs, the other one cannot occur at the same time. They're separated out. Disjointedness, mutually exclusive, is usually represented with or. Not always, but usually. So you think or goes with disjoint. You got to memorize this definition because it shows up again and again and again. Okay? Moving on. If two events are disjoint, and that's first has to be established, then you can go ahead and add them. So the example I had, you can read that through again. I'm assuming you guys have read this. But that's the main point. If they're disjoint, they're separated out, then and only then can you add up those probabilities. If you don't have that definition, you try adding up the probabilities, you're going to get into trouble. Okay, now the other major definition is independence. Independence goes with multiplication, but you first have to establish independence. Independence, the idea there is they're not separated out like with mutually exclusive. It's slightly different. You're basically saying that there's no memory. So independence, if you remember the previous definition from last lecture, there's no memory, things are random. These are some of the key words given. So if you toss a die 2 times, it's independent. One has no memory of the other event. When that happens, when you're given independence, you think you want to multiply them. So multiplication comes in, not addition. I'm giving you all this as a general, this is a lot, don't worry about it. I'm just laying the groundwork. What we're going to do is practice. The practice is crucial because only through the practice will you start to get a feel for how these definitions work. You cannot, again, just sit back and relax. That's not the way logic works. It's exercise heavy. You got to do. You can't sit on the sidelines and think, no problem, I'll get it later. You have to actually exercise and do it to acquire these skills. It is a skills-based course. That is part of logic and why it's hard. Okay, the tricky case diagrammed in the book. Again, if you read this out and you're confused, good, but at least you tried it out, you read it. So I'm going to go through this a bit more carefully. There are two urns. The urns are containers. Like if you're, I don't know, if it's like one of those games, bingo, for example, the urn would be that pot that they have. They mix it up, the balls are bouncing around, and the person goes in and grabs it out. Okay, so this is what's called a canonical problem, meaning it's a standardized problem that helps illustrate a whole series of other types of problems. So there are two containers, two urns. U1, urn 1, has 3 red balls and 1 green. Urn 2 has the opposite proportion, 1 red and 3 green. The idea here is you then toss a coin to determine which you draw from. If you get a heads, H, you draw from urn 1. That's the rule. If you get a tails, you draw from U2. This is the way the problem's set up. So you toss a coin, first branch, if you get heads, you draw from urn 1. Urn 1 again, 3 red, 1 green. The other branch, if you get tails, you're drawing from urn 2, 1 red, 3 green, right? That's just the proportions. Okay. Probability of 2 reds, that's what the book asks about first off, is actually broken down into 2 disjoint events. Why? Because there are 2 ways in which you can get 2 reds. You can either first draw from urn 1 and get 2 reds. You get 1 red and then draw again. Or you draw from urn 2 and you get 2 reds. Okay? Because they're disjoint, meaning why? Why disjoint? Remember, the definition of disjoint is if one event occurs, the other one cannot occur at the same time. So if you're drawing from urn 1, you can't simultaneously draw from urn 2 at the same time. You're on a different branch. So that allows you to add. And then secondly, when you draw from urn 1, let's say, and you get a red, and then you put that red back and you mix it up, it gets re-randomized, so no memory, and you draw again, each of those draws is independent because there's no memory of the previous red draw, right? That's the idea. You put the ball back into the urn. If it's one of those bingo machines where the air's blowing and it's bouncing them around, the idea is there it's mixing it around. That randomizes it, or another way to say it, it erases the memory. Or it thinks of cards in a deck. If it's shuffled properly, and this is a big if, and we can get into this a bit later, it's supposed to erase the memory of the card deck. So in Vegas, they have, instead of people doing it because there's errors made, they have machines that are supposed to mix it up so many times to erase the memory so you get independent draws. Oh, for those of you who gamble. If not, oh, all right, moving on. So here's the final computation. What's the probability of 2 reds? That breaks down to the probability of 2 reds from urn 1, or, that's the branching, because you can get, there's 2 ways to get 2 reds, or you get 2 reds from urn 2. That equals the probability of 2 reds from urn 1 plus. Why plus? Because remember, we established that they're mutually exclusive. They're disjoint. Disjoint with or allows for plus. Remember, or goes with plus only if they're disjoint. Or goes with plus only if they're disjoint. You gotta hammer that stuff home in your head. I know it's a lot. Plus the probability of 2 reds from urn 2. That equals, in turn, when you read this off the diagram, 1/2, that's the probability of getting heads from drawing from urn 1, times 3/4, which is the probability of getting a red from urn 1, times 3/4, the probability of getting a red from urn 1, plus 1/2, the probability of getting tails you're drawing from urn 2. Remember that we had to first flip a coin, times 1/4. There's only 1 red out of 4 total balls, so 1/4 probability of getting a red times 1/4. When you do all this, it's 10 out of 32. So here's the bottom line. You multiply events that are independent, and you add events that are disjoint. And then to establish that they're disjoint or independent, you got to apply the definitions. Okay, that's a lot, but what we're going to focus on, this is just the general lecture. What we're going to focus on, especially the next time, is practice. So make sure you try some of the problems at the back of the book for this chapter. I'll go over that in the next lecture, and as well as we got some extra problems for practice to try and exercise your thinking through this new technical language. See you folks next time. Keep up with the work.